Today we're going to introduce the idea of charge. So the ancients discovered an effect. If you take a piece of amber, and basically amber is, if you slice or cut a pine tree, that sap that flows, if that hardens, that becomes what we call amber. And if you take a piece of amber and you rub it on a cat fur, I don't really know how the ancients discovered this, but you get a strange effect. The amber, so here's a block of amber, it attracts light objects, so feathers or some crushed leaves. And this was called the amber effect. So this was known from ancient times, that if you take an amber rod and you rub it on some animal fur, it acquires something that attracts light objects. And that was called the amber effect. So it turns out that in Greek, the word for amber is electron. And so it was also called the electron effect if you were a Greek speaker at the time. Electricus is the adjective, which means of amber. And so that's kind of where we get the words from. And people sort of thought, even all the way through the late 1800s, that this stuff, until the electron was discovered, was associated with amber. It was created when the amber was rubbed. So generally the word electron meant the stuff, and the flow of it was called electricity. In 1897, the actual carrier of charge, a particle was discovered, and after that we use the noun electron to refer to this particle. But that's kind of where the word comes from. Kind of interesting history there. Now, this property of matter that's associated with this fact we call charge. And so an electron is a carrier of charge, but charge is the property. And there are 7 fundamental charges in nature that we can't define in terms of anything else. And charge is one of them. So to kind of review a little bit, put some things together maybe we've talked about in the past. Some quantities we've already encountered are length. We can't define length in terms of anything else. We just postulate that it is. We took a stick, we called it a meter, and we said that length is a meter, but we couldn't really define or explain what exactly length is in terms of anything else more fundamental. So we call that a fundamental quantity. Mass, the amount of matter, is also a fundamental quantity, and so is time. You can't really define time. It's how much time passes. Or it's how long something takes, which is just a circular definition because you're really just saying it's a measure of time. So things like velocity, though, velocity is a length divided by a time. And so when you're talking about a velocity, you can talk about length divided by time, and acceleration is a velocity divided by time. So that's length divided by time squared. A force is a kilogram meter per second squared, so we can define forces in terms of these 3 fundamental quantities. We can define energy, which is a joule, which is just a kilogram meter squared per second squared. And so we can define all these things we've already covered in terms of these 3 fundamental quantities. So we say that velocity, for example, is not a fundamental quantity. It's a derived quantity that depends on these 2 fundamental, length and time. So we're going to encounter a new one today, and that's charge. So we can't really explain charge in terms of anything else. It's just a fundamental quantity. It's just a property of nature, like mass, which an object has, it possesses, and due to this property, some interesting things happen. There are some forces of interaction and stuff, similar to the way that mass produces forces in the form of gravity. Another one we've already encountered is temperature. And that's a fundamental quantity, the absolute temperature, the thermodynamic temperature. Another one is the amount of matter, which is the mole. You've encountered that in chemistry. And the last one is luminosity, or the luminous intensity, measured in candela. And that's just another one that we will discuss later in the next unit when we talk about optics and light. So it turns out that if you take a piece of glass and you rub it with silk, you can also produce an electric charge, but this charge turns out to be exactly opposite the charge that is produced by the amber in the fur. And so that's a new kind of charge, which is the opposite. So Ben Franklin decided that he would call these positive and negative charges, these 2 different charges. It's really an arbitrary choice. We could have called them up or down. We could have called them vanilla and chocolate, but we chose positive and negative. And we know that positive charges repel each other. 2 negative charges repel each other, but if the charges are opposite, they attract each other. There's an attractive force between there. So here's a quick little demonstration that's kind of interesting. It's from the PhET website. And take a second to load here. What you've got is a balloon, and charges are always paired up. A positive charge and a negative charge are usually paired up in nature, and we say that that is neutral. Not because that there's no charges there, but because there's no excess charges. Now, it turns out if you take a rubber balloon and you rub it on a sweater, or maybe your hair if you have some, you can steal some of the electrons from the sweater. And so now the balloon has an excess of negative charges, and the sweater has an excess of positive charges, and there's a force between them. So the balloon is actually attracted to the sweater. We call this an electrostatic force because these electrons themselves are not moving relative to each other. Um, but it's a pretty cool effect. And if you keep rubbing, you can get a whole bunch of electrons. And so now there's a very large negative net force charge on the balloon, and it's pulled towards the sweater, and you get static cling. So this happens with your hair. This happens with your sweater. In the wintertime, turns out that if there's some humidity in the air, those negative charges can jump off the balloon and hop back on the sweater without having to move the balloon. So in the summertime, it doesn't work so well. If I bring this balloon over here near the wall, then all the excess negative charges repel the negative charges in the wall. Now remember, the negative charges can move. They are associated with electrons, which can move. The positive charges are associated with the nucleus, and the nucleus cannot move. It is locked in there in a solid. So you can actually take a balloon, rub it on your head, and make it stick to the wall. So that's an example of how these forces work. Okay, so here we are. The law of charges. We can detect a charge with a clever device called an electroscope. We have one of these at school, but you can't see it because we're not at school. So it's basically a piece of metal. There's an insulating rubber stopper here, and that metal is attached to two gold or foil leaves. They're just very thin pieces of tin foil in our case. We don't have the gold version. And this can use to detect charge. So to kind of show you how that works, here's a little applet, which will help us kind of visualize what's going on. So I take an amber rod, I rub it on some cat fur, and I steal some of the electrons off of it so it has a net positive charge. So here's my amber rod with a net positive charge. If I bring it near a conducting dome, and my dome originally has positives and negatives all connected together, what happens is when I bring it near, all the negative charges are attracted to the positive charge on my amber rod, and they move because negative charges on a conductor can move. Electrons can move on a metal. So they come up here near this edge, and that leaves a net positive charge on the backside. Okay, so that's called induction. Okay, now let me reload it because I haven't paid for the subscription. So I only get 30 seconds. Okay, here's what happens with an electroscope. Same thing, I've got a little dome of metal, and I've got a piece of metal going down, and then there are two leaves. When I bring this positive charge near, the negative charge in the metal slides up towards the dome, and that leaves positive charges down here on the leaves, and those positive charges repel each other, and the leaves fly apart. So if I bring a positively charged object near my electroscope, the leaves fly apart, and if I take it away, they disappear or they fall back together. Okay? So that's how we detect charge with an electroscope. So it's a simple tool to detect charge. You can't detect whether it's a positive or negative charge. All you can do is detect whether a charge is present. So if I were to rub my head on a balloon and bring it near this electroscope dome, those leaves would fly apart. I don't know whether the balloon is positively charged or negatively charged. I just know there's a charge there. Okay, so now the question is, how big are these forces? And we're going to do a lab to investigate this. So we have two charges, and we'll call them Q1 and Q2. So in physics, we use Q as the variable for charge. And I want to know, there are forces between these charges, but how does that force depend on the size of the charge? So I'm going to look at Q2 here. If I make Q2 bigger and bigger and bigger, what happens to the force between these two charges? So we're going to use a simulator to investigate this. We can't really use actual experiments because we can't control the charge on a balloon very carefully. And it's very hard to get an accurate amount of charge, and it's also very difficult to measure the force between them. So we're going to be doing a simulation here. So the first question is, how does this force depend on the size of the charge? And the second question will be, how does the force depend on the distance between the centers of these two objects? If I make them farther apart, does the force between them get bigger, smaller, or maybe stay the same? That's the question. So in Lab A, we are going to ask, how does the force depend on the charge? Since we're asking, how does the force depend on the charge, the force is going to be the dependent variable. It's going to go on the y-axis. And the size of the charge is the independent variable. It's what we control. It's going to go on the x-axis. So you're going to collect some data and try to find a mathematical model. The second question we're going to ask is, how does this force depend on the distance? So again, the force is the dependent variable. It goes on the y-axis. We're going to vary the distance, so it's the independent variable. It goes on the x-axis, and we will look for a relationship there too. Okay, so part A of the lab is going to be to ask, how does the force depend on the charge? Part B of the lab is going to be to ask, how does the force depend on the distance between them? So let me quickly show you just kind of how the lab goes. We're going to use a simulator. There's a link to it in your lesson, but when you first load the simulator, you're going to get a screen that looks like this. We're going to use the macro scale. So a couple things to note. First of all, you can move the charges. So it's probably easiest if you move the left charge all the way to the left. The right charge can also move. And in part A of the lab, we're going to keep the distance between them fixed. So the lab will tell you what distance to make it. Let's say the lab tells us to make it 4.6 meters apart. So we've got to very carefully make sure that the left side of the ruler is right on the middle of this charge, and the middle of the red charge is going to be at 4.6. So each of these is 0.2, so there's 4.6 centimeters right there. You're going to fix charge 1 at whatever is specified in your lab. And then you are going to vary charge 2. So start at 0 and then make charge 2 1 microcoulomb and 2 microcoulombs and 3 microcoulombs. And each time you're going to record the force, and then you're going to look for a math model there, okay? That's the first part of the lab. The second part of the lab, you're going to keep charge 1 and charge 2 fixed. So those are going to stay whatever you're told to put them at. And you're going to vary the distance. So the smallest you can get the distance between these two guys is 1.4 meters. Okay, so remember each tick here is, 0.2. So you're going to be 1.4 centimeters. That's the closest you can make them. The farthest you can make them apart is 10 centimeters. And so you're going to pick a couple of different points along here, and you're going to record the distance between them, and you're going to record the force, and you're going to try to find a mathematical model. Once you find math models, once you've answered the questions, how does the force depend on the charge, and how does the force depend on the distance, then we're going to move on and look quantitatively at what is called Coulomb's law, which tells us how to find the force between any two charges. Okay, so next step is to do the lab, and after you finish the lab, you'll come back for another lesson and then some problems to solve.